All right, hi there. This is Jacob Nash, and in this video, we'll be talking about the squeeze theorem for calculus. So we're just going to be looking at this on a basic level, but the first thing that we're going to want to look at right here is a more basic theorem, and this is what we can use when the squeeze theorem doesn't work, because theorems do not always work. If this always worked, then this is what you would always want to do, but it's not always what works. But here's what the basic theorem says, and I'll say it in more simple terms after I read this. But if a function f of x is less than or equal to g of x when x is near a, except possibly at a, then the limits of f and g both exist as x approaches a, and the limits. If that's the case, then this is the case, which is that the limit will also be less than or equal to. So we're basically saying, considering these conditions, if f of x is less than or equal to g of x, then the limit of f of x will also be less than or equal to the limit of g of x. And this can apply to more than two functions as well. For example, if there is also an h of x applicable. And we'll look at this will make more sense when we look at examples, but this is just something that is good to know. But it's saying when x is near a, so that's important to say because near a point, that's what a limit is. Except possibly at a, they put that in there because there can be a hole, so there can be a limit when the actual point doesn't exist. So that's why it says that. Now, the actual squeeze theorem states this. If f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a, except possibly at a, like I said, we have to say that just in case, um, then, or sorry, not then, and, so that has to be true, and this. The limit of f of x as x approaches a equals the limit of h of x as x approaches a, and they both equal the same thing, which is any number L, then the limit of g of x as x approaches a must also equal L. So we're kind of just saying if the limits of f of x and h of x equal each other, then g of x, the limit of g of x will also have to equal that same number as long as this is true. So if this doesn't make sense, well, that's okay. Let's see how we can use it. Well, how do I know if I need to use it? That's probably what you would wonder first. It is good to use if factoring or using conjugates don't work to get rid of stupid things, which means a denominator of zero, something that would make a denominator zero. Remember, um, that can happen sometimes. We're trying to find the limit. If it's a polynomial, you can plug in. If it's a rational function, you can plug in, except if it would make the denominator zero, which that happens often in problems you get. Um, so the two things that we've learned so far, well, that's kind of bad for me to say because I don't think I have the videos up yet, but this video should be watched after the one of factoring and conjugates. Um, uh, that's what we would normally want to do. We could try to factor and cancel things out, or we can do a conjugate if there's a dumb square root. Then you do a conjugate. But if those things don't work, which sometimes that's possible, and then you would want to use this. And if the question begins with an inequality of three, meaning that it already starts out with an inequality, then you might want to use it. And you'll see what I'm talking about. But remember, this doesn't always work. I'll show you examples of where it does work and one where it doesn't. Well, here's one where it does work. Now, you might look at this and just be like, oh, I hate that. That looks horrible, super hard. Well, fortunately, not that hard, actually, as long as you know how to do it. So there's a lot of things like this in math where it looks stupid and hard, but it's actually not. But what do we do first? Okay, well, first of all, pretending like we didn't know that we're going to use squeeze theorem, how do I know that this is what we're going to have to do? That goes back to what was on this slide. Okay, I see. What would I normally want to do? I would want to plug in this 0 into x. All right, if I do that, I get a 0 here, not bad. If I do this, bad. Pi divided by 0, not a thing that we can do. Um, and you can't just stop there and say it does not exist. Can't do that. So sorry, that's not how simple it is. Um, well, then what do we do? Are we able to factor? No, because there's only this. Um, are we able to do a conjugate thing? No, that's not what we do unless there's square root. We might want to consider using the squeeze theorem because there's nothing we can do about that stupid x in the denominator without using higher level stuff like arc sine, which we don't need to do. So forget about that. We're just basically saying that's all we can do at this point. And if it doesn't work, then there's still something that we can do. But this is an example where it does, so it will work. But what do we do first? We do this. This is what you need to do every time when you see something like this. You, when it's sine, because a sine function, you might not know what this graph looks like, um, but any sine graph, it has to be between -1 and 1. That is what it can be. And it could be those numbers too. That's why we put the equals under those inequality signs, because it could be exactly -1 or 1, but it's going to be in between them or them. And what you always do is you take this part, you get rid of all the things that are beside it. So no more -1, don't need that. No more x squared, just this middle part right here. We're going to put it in between -1 and 1. That's what we start out with. Now our goal is to make this middle part right here the same thing as this problem. So you might be like, oh, I'll just put it there then. No, because that's not how it works. Remember back to basic algebra. For inequalities, you have to do the same thing to all three. Well, all two or three, however many there are. So we want this part to be the same as this whole thing eventually with the x squared and -1. Right now it's not, so we have to figure out what we can do. We have two different things, the x squared, the -1. Which one do we do first? This, because it's multiplied. You know, PEMDAS, remember that, like order of operations. We're going to want to do this first. So we have to multiply x squared on all three sides. So x squared there, x squared there, x squared there. Then you see what happens down here. We have a negative x squared. We have x squared times sine of pi divided by x, and then we have x squared here. Now, the next step would be to add this -1, well, subtract 1, whatever you would say, put that on there on all three sides. There you go. And now, yay, those two things are the same. Remember, our goal was to make the middle thing. Sorry to not be so good with my terms, but that's not the purpose of this video. Like, I don't need to overcomplicate things. The middle thing is the same. See, this part is the same as this. Okay, well, how did that help us? Now what do we do? Well, remember what the squeeze rule says, the squeeze theorem says, that if the limit of these two are the same, then the middle one must be the same. So we have to take the limit of this one over here and this one over here and see if they're equal. All right. What we have to do is, since it's polynomial, we can just plug in 0 for x. And for both, we result in -1. Sorry to kind of skip some steps, but for time's sake, I can't just go crazy and do everything. So as you can see, I just plugged in 0 for both of these, and that's this left and this right. And they are the same. Therefore, by squeeze theorem, this middle one, which is the same as this original problem, is equal to -1. You have to say by squeeze theorem, okay? That's really important. That's why I underlined it in red. But the answer is -1. So we have a simple answer, even though this thing looks stupid. But just to review, what steps did we do? First, we created this inequality. We put -1 on one side. We put 1 on the other. That's always how it is, by the way, because that's only what a sine function can be. In the middle, we just took only the part that has sine here. Then we can't forget about these two things. We add them on. do it to all three sides. Then this left and right, we see if they are the same, and they were. And because of that, that means this middle one is also the same because going back to this, that's what the squeeze theorem says. Okay. All right, another one. All right. Well, how about this? Well, this time I will work it out. Okay. So if you already got what you needed from this video, you can exit out. But if you'd like to see another example, then take a look at this. And it looks crazy, but it's actually not that bad. All right, let me see. I'm gonna try to do the best I can writing with the computer. So first of all, how do we know that we need to do squeeze theorem? Well, we have something stupid. We have this 2 pi. I don't know if you can see my cursor, sorry. Um, we have this 2 pi. You see limit of x goes to 2 pi. Um, that if we plug that in for x, we would end up with a denominator of 0. See that sign part? One, it would end up 1 over 0. So that's how we know that there's a problem. Normally, we might want to factor or do conjugate, but neither can we do. Because trigonometric function, we cannot do something that's in this argument right here. So this looks like a horrible problem, but it's just they do things like this to try to trick you. So they make you think it's harder than it is. Remember what I say though. You have to start out with making an inequality. Okay. That's pretty frustrating. Um, First time using this, so bear with me. All right. I was on a line feature instead of draw. So we're going to make an inequality right here. Now, what do we put in the middle? Only the thing that has sign with it, which is that middle part there. So sine, my handwriting is not going to be the best, so sorry. That's why I had the other one already worked out. Sine of 1 over x minus 2 pi. We did that? Good. Now what? Remember, our goal is to make it turn into this whole thing. So we can't forget about this first part, x minus 2 pi to the 147th, or the plus 3. But we do this part first because it's the multiply. So you just put that on all sides. So we have to multiply all three sides by the x minus 2 pi to the 147th power. So we do this here. I'll pause it for now so you can see. And they'll have to wait. Okay, so as you can see, I did that to all three sides. Now we can't forget about this plus 3. For time's sake, I'm not going to rewrite that whole thing. I'm just going to put plus 3 on all three sides because that's what we have to do. And what do you know? Now, this is the same as this. And that's what our goal was. But you can't just do that in the first place because, like, what about this? Like, that would be creating a false statement. You can't forget about those two. So that's, as you can see, what ends up happening pretty much is that it's just all the things that are not this, and one is positive and one is negative. But you still need to show all your work. That's important. Some teachers especially would take off points if you didn't. So now what do? We have to see if the limit of this and the limit of this are equal. And if they are, then the limit of both of them will be the same as this. So we're going to have to do this. Write this down. The limit of x, or sorry, the limit as x goes to 2 pi of, for time's sake, I'm not going to write this whole thing. Let's just call this A. Let's call this C. So we'll just say A right now, A. Now, what is that? Is this a polynomial? In fact, it is. So we just can plug in 2 pi and you might just be like, oh my gosh, like I don't even know what that equals, 6.28. Well, don't even have to do that. I know you can't use a calculator. All that it is, if you plug this in, would be 2 pi minus 2 pi. That is 0. Negative 0 plus 3, there's not even a negative 0, so that's just 3. So the answer is 3. Now, we have to do the other one too. The limit of as x goes to 2 pi of c, or basically this part. Okay, plug in 2 pi. 2 pi minus 2 pi equals 0 to the 147th power. Sorry, I forgot that over here, but 0 to the 147th power is still 0. Plus 3 is 3. And yeah, so the 147 might have freaked you out, but it ended up not even mattering. So now both of them equal 3. So we can say by squeeze theorem, just pretend like that says theorem. Um, the limit of this is equal to 3. So that's another example where it looks really hard, but the answer is just 3. Um, you have to say by squeeze theorem. All right. Now let's see a different example, a different type of problem. What do we do for this? Okay. So this problem saying if x plus 1 divided by x squared minus 1 is less than or equal to f of x, which is less than or equal to e to the x minus 2, then what is the limit of f of x as x approaches 2? When you first see this problem, you might just be like, excuse me, what do I do? Because that looks horrible. Well, actually, it's not that bad. Um, so we might know, how do we know we would use squeeze theorem? I said, remember, back on the other slide, if you see something like this, like 3 things, you might just think, okay, I might have used squeeze theorem. So they already did the work for you in this case. So what exactly do we have to do here? Well, it's the same thing as before. We just don't have to do the first step. We have to see what the limit is of this and what the limit is of this. And if they're equal, then the limit of f of x is this. So let's start that out. The limit of x plus 1 divided by x squared minus 1 as x approaches what? What do we put there? 2, because that's what the question is asking. What does that equal? You might think, oh, denominator of 0. Well, it doesn't happen this time because if you plug in 2, we would get 2 plus 1 on the top, which is 3. 2 squared, 4 minus 1 on the bottom, 3, which is 1. So now let's do the other part. Limit of e to the power of x minus 2 as x approaches 2. Now, to be clear up here, you can plug it in if it works, and it does. It doesn't make us have a denominator of 0. So that's why I was able to do that. Now here, it would end up being 2 minus 2, which would be e to the 0, which anything to the 0 power is 1. So once again, they've thrown something dumb like that to try to throw you off, but didn't matter. So both of those are the same. So by squeeze theorem, and I will just write ST for now, but you should never do that. By squeeze theorem, the answer is 1. Remember to always put that and actually write out squeeze theorem. So that's a simple problem, right? That's even easier than the last. Um, but that's just showing you a different format that the problem may be in that you might see. Now I will show you an example where it doesn't work. Now this looks the same as the other one that we just did, and there is only one difference. This time, the limit is as x approaches -1. So we'll do the same thing as last time. We have to find the limit of this and the limit of this and see if they're equal. And if they are, then that's the answer. Um, so that's bad color. Sorry about that. Limit of x plus 1 divided by x squared minus 1 as x approaches -1. All right, well, let's try that. 1 plus 1, or sorry, -1 plus 1, 0. -1 squared is +1, -1 is 0. Not good. Divide by 0, not a thing that we can do. So that causes a problem, doesn't it? So now we'll have to do something like squeeze theorem on top of a squeeze theorem. Luckily, we don't have to do that. We can just factor. So you always have to write the LIM. Don't forget that when you're doing your work. That would be x plus 1 on top. Oh, I'm sorry, this thing writes so horribly. And then what are the two factors that we end up with? It's a difference of squares. So x plus 1, x minus 1. If you don't remember difference of squares for whatever reason, I do have a video on that. Just look up Jacob Nash difference of squares. All right. Now we will x out these two. They can cancel out. But if I just rewrite this and simplify it, that actually isn't true. So we have to put something, a little thing here that says where x does not equal -1. So what I'm about to write is only true for where x doesn't equal -1. So this right here is crucial to write, or else you are writing a false statement. So we're only left with 1 on the top because there's nothing. X minus 1. Now let's plug in. Don't have to write the LIM when you plug in. And we end up with -1/2. All right, let's see if this ends up being the same for the other part. Okie doke. We'll plug that in. Does that cause us any problems? E to the -1 minus 2. No problems, but we do get a stupid answer that you don't have to actually just give a decimal form. I don't think that's even really possible to do in your head because it's approximately 2.71, but it's not a number that it has a continuous decimal, so that doesn't help us. These two things are different, so we cannot use the squeeze theorem. Now pay attention to this. You might want to say, because of this, it does not exist. You might be tempted to write that. But the thing about theorems is if it doesn't work, it doesn't mean that the contrary is true. So just because the squeeze theorem doesn't apply doesn't mean that it doesn't exist. Because actually the original problem that this is that I didn't create, it's supposed to say that f of x does exist. So it does exist, but how do we even figure out what it is? Not possible. At this level that we are right now, um, this is not possible. So what we have to instead write is just simply this. Remember, this was the limit from the left, or not from the left, sorry, this first left part. And then we can just write, oops, limit of f of x as x approaches -1. And then e to the -3. This statement is true. It doesn't give us an exact answer, but that is acceptable. That's what you would have to say. So when it doesn't work, you end up doing this. And you might think to yourself, why? I thought we couldn't use the squeeze theorem. Well, actually, that goes back to something I said at the beginning of this video. Let's go back to see. Remember just this basic theorem. If f of x is less than or equal to g of x with these conditions, then the limit of f of x is less than or equal to g of x. So if we go back over here, we know that that's true because it says it right here. We just found out the limits of those two, which were -1/2 and e to the -3. So based on that theorem that I started out with, it's not actually the squeeze theorem. It's just a different theorem. And remember, I said you can use this when the squeeze theorem fails. That's how we were able to say that, because I said it can apply to more than two functions. So in this case, it was 3. So f of x was in the middle since f of x is in the middle for this part, for the limits, it will also be in the middle. So that's why that's the answer. So that's it for this video. I know that's a little crazy, but hopefully the more practice you do, the better. So just I'm sure you might have some homework or something like some problems to do, and the more practice, the better, and it becomes easier. But squeeze theorem is a very important thing in math to know, and that's what it was for you. Thanks for watching.